Hello and welcome. In this video, I want to take a look at the notion of a flux integral across a surface. Now, this is very much like what we've already done in the plane, where we did both the line integral of a vector field along a curve, and we did the line integral of a vector field across the curve. And across the curve we called flux, and this will be very much the same as that flux integral. So this is what it was when you had a parameterized curve C. F was a vector field in R2. N was a unit normal vector to the curve, and ds was, of course, a little bit of arc length. Okay, and this was essentially the normal component of the vector field at each point along the curve, multiplied by a little bit of arc length, and you add it all up. Okay, that was called the flux integral. Now we're going to do the same thing in R3, but we're looking at going across the surface rather than going across the curve. Now, in the plane, there was for each curve, there was a uniquely defined unit tangent vector that moved with the curve. And so it made sense for us to be able to do the integral of the vector field along the curve, and we could then rotate that unit tangent vector to get a unit normal vector, and then do these flux integrals across the curve. In R3 with surfaces, we don't really have the notion of the integral along the surface, because at any point on the surface there's a whole plane worth of directions that are tangent to the plane or parallel to the plane. And so to move along the surface, there's not a unique direction. However, there is a unique direction perpendicular to the surface, and that's what we call the normal vector. So we will have a flux across, but we won't have the vector field along the surface. So here we go. If we're given a continuous vector field, we're going to call that F. I didn't seem to name it here, but given a continuous vector field F on a region D in R3, and that region contains a surface S, where S is parameterized by some vector function R of u and v, then we define the flux integral as, it looks like a double integral over the surface S of F dotted with n d capital S. Now, n is a unit normal vector, which is essentially it's a continuous vector field on the surface. You have to have an orientable surface in order to do that, because otherwise you wouldn't have a continuous normal vector field. But in the case that you do, we do it. We dot it. And the d capital S here is a small amount of surface area. Just like up here, the d little s was a small amount of arc length. So we're taking the the perpendicular component of the vector field and multiplying it by a little bit of area and then adding that all up. Now, we write it this way as well, F dotted with d capital vector S. This is a lot like we did for line integrals along the curve, where we had the unit tangent vector times a little bit of arc length and decided that that was just the derivative vector times dt. So we just called that d little vector r, but now I'm calling it d capital vector S. And here's the reason. The little bit of arc length, d capital S, we saw from before was the cross product of the partial of r with respect to u and the partial of r with respect to v. Take the length of that times a little bit of area in the uv plane, little dA. Now, RU crossed with RV is definitely a normal vector, because RU and RV are parallel to the surface, tangent to the surface, and so when you cross those two, you get a vector that's perpendicular. So we can make that a unit vector by just dividing by its length. Okay, so right here we're dividing by its length. So this n times ds, this is n, this is ds, so it's this times that, and the lengths of RU cross RV cancel out, and you just end up with the vector, which is RU crossed with RV. This is not a length anymore. This is the vector, RU crossed with RV, times dA. So this is a a vector, but it's sort of a differential as well because it's got the dA in it. So we're just calling it ds. It is the vector. It incorporates both the normal vector and that little bit of surface area that we want to multiply in. Okay. So now we have that this flux integral, n dotted with ds, can be written this way, which if we now convert that all to u's and v's, you're evaluating the function on the surface, the function of the vector field on the surface, and you're dotting that with this ds right here. So Ru crossed with Rv times dA. And the limits of integration are going to be whatever the region D is in the UV plane. Okay. So let's do one example. Here we go. So I'm going to let the vector field be x squared comma y squared comma z squared. This is actually one of the even numbered questions in the textbook homework. And I seem to have some words left out, but let this surface that I'm integrating over be the part of this plane here, z equals y plus 1, that's inside the cylinder, x squared plus y squared equals 1. Okay, so there's the picture, and I don't want all of the plane, I just want the part that's inside the cylinder. So if we take a look at this in place we can move it around, right? You can see I just want the stuff inside there. And you can see the vector field kind of pointing off in all sorts of weird directions. I do notice that, you know, it is crossing the surface. So I guess it's crossing this way down here and this way up there. But it looks to me like there's probably more up than down. I say, so I'm expecting a positive result here, although the result depends on my choice of normal vector. Am I pointing the one that goes up or the one that goes down? And that's going to determine whether I get a plus or a minus sign out of this result. And to say Ru crossed with Rv is always giving you the same thing, it's not necessarily, because the mapping from the UV plane onto the surface may take those two vectors, Ru and Rv, and put them like this, or it may take them and put them like this, in which case the cross product is one way or the other way. It's not immediately obvious which one you're getting. So anyway, the simplest way to parameterize this plane is this one that I have right here, where x is u, y is v, and z is v plus 1. So z is y plus 1 like they wanted. However, from the point of view of the integral that I'm going to have to do, because I'm going to have to integrate over just the stuff on the inside of that, it's like I'm going to choose to essentially do this in polar coordinate or maybe in cylindrical coordinates. So I've got a different parameterization that I'm going to use, and that's the one right here. Turn this one on. Actually, as I turn it on and off, watch inside there. So there's off and on, and you can see that this sort of spiderweb grid comes in there. And if I turn off the other one, I have that plane, but now I have it just inside of the cylinder. In fact, you can see it sort of overlapping just a little bit where the cylinder's not being drawn properly. So what I have here is x is u cos v and y is u sine v. So I'm thinking of u playing the role that r usually does, and v is playing the role of theta. But then, of course, we want z to equal y plus 1. So where y is u sine v, I'm making z equal to u sine v plus 1. So z is u plus 1. So I'm describing that surface, but my parameters are more in line with polar coordinates than they are with x's and y's. And that's going to make it easy for me to describe the region in the UV plane that I'm interested in, because what I'm doing is u is going from 0 out to 1, and v is going from 0 to 2 pi. Right? So in the UV plane, this is a rectangular region. it's being mapped into this circle here in the X, well, I guess it's an ellipse, circle with respect to X and Y, and then tilted with respect to Z, right? So that's the surface I'm going to integrate over. I'm going to dot it, I'm going to get the normal vector to it, I'm going to dot that with the vector field, and then multiply by a little bit of arc length, a little bit of surface area, and add it all up. So here we go, let's go back and do that. So here's my parameterization. U cos V, U sine V, U sine V plus 1, where U is between 0 and 1 and V is between 0 and 2 pi. So the partial with respect to U is cos V sine V sine V. The partial with respect to V is minus U sine V, U cos V, and U cos V. So to do the cross product, I need this one crossed with that one. So the first component is U sine V, sorry, it's sine V times U cos V. So that's the U sine V cos V. And then minus sine V times U cos V, which is, again, the same thing. So that actually turns into a 0. The second component here is sine V times minus U sine V. So that's the minus U sine squared V. And then I've got cosine V times U cosine V. So that's the minus U cos squared V. That one, the minus u's cancel out. The sine squared V plus cos squared V is 1. And so that turns into a negative U. And likewise on the last one, where I do U cos V times cos V minus negative U sine V times sine V. And this turns into a positive U. Okay. So there's the cross product. Now, now I think I'm ready, because the flux integral is going to be the vector field evaluated at points on the surface dotted with this normal vector times dA. And so here we go. There is, remember, the vector field was x squared comma y squared comma z squared. So this first part is the x coordinate here, cosine V squared. Sorry, that was the wrong one to look at. This was r, so this x component squared, and then this is the y component up here squared, and this is the z component from the parameterization squared. Be careful I don't look at the derivatives when I want the actual function. And I'm dotting that now with ru crossed with rv, which we already determined was that. And this is du dv, where u goes from 0 to 1 and v goes from 0 to 2 pi. Take the dot product. What happens? Yeah, this is, okay, so the first one is times 0, so that goes away. You then get a u squared sine squared times negative u, so that's the negative u cubed sine squared v. And then here you're going to square this out and then multiply it by u. In particular, that first term is going to be a u cubed sine squared v, and that's this one, and that'll cancel with that one. The middle term will be a 2u sine v, but then it gets multiplied by u. So that's a 2u squared sine v, and then the 1 squared is 1 times u is u. Okay. So the first two terms cancel out, and you've got the integral here of 2u squared sine v plus u, and I integrate here u first on the inside, plug in the 1, plug in the 0, subtract, and then you've got the integral of this thing, which integrates to negative 2/3 cosine v plus v over 2. So I plug in the 2 pi to get negative 2/3 cosine 2 pi plus 2 pi over 2 minus what I get when I plug the 0 in, negative 2/3 cosine 0 plus 0 over 2. So the cosine of 2 pi is 1, so I get negative 2/3 plus pi. And again, this is a 1, so I get a minus 2/3 plus 0. And the minus 2/3 and plus 2/3 cancel out, and the answer here is pi. That the flux across that surface for this vector field is pi. There you go. You try some of these in the homework. They're very similar to the flux integrals we did for line integrals, but they're just double integrals now. So much more fun. Enjoy.